Welcome to lesson 2.3. We're going to get into polynomial functions and their graphs. So some of this will look familiar, but a lot of this will be, we've talked a lot about how a lot of what we've been doing so far has been, uh, a review of Algebra 2 topics. We're definitely getting some new stuff here. All right, so there's a lot in the objective. Ultimately, the goal is to graph polynomial functions, but all of this is going to go into it. So let's just read through it one by one. Identify polynomial functions, recognize characteristics of graphs of polynomial functions, determine end behavior. We'll talk about what end behavior even is. Use factoring to find zeros of polynomial functions. That's a skill that we learned last year, but we'll use it here. Identify zeros and their multiplicities. Again, some stuff we did use last year, but we're going to use it in a different way here. Use the intermediate value theorem. So it's a new theorem, pretty straightforward, but we'll talk about that. Understand the relationship between degree and turning points. So we'll look at that. And then ultimately graphing polynomial functions. So every one of those bullets leads you to the end result there, okay? So we're building our way to being able to graph at the end. So everything we're doing, those are the trees within the forest of graphing polynomial functions. The first thing to talk about, here's the definition of a polynomial function. Really, I don't want you to take much more out of this other than this is a polynomial function of degree n, because n is the biggest exponent of all of the terms there. And the coefficient of that term with the highest exponent is considered the leading coefficient. Okay. Polynomial functions of degree 2 or higher have graphs that are smooth and continuous. Smooth, by definition, is a graph that has curves and no sharp corners. So think of a quadratic function as opposed to an absolute value function. A parabola is smooth, an absolute value function is not. By continuous, we mean the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. So again, a quadratic function is continuous. There is no breaks in that parabola, right? And same with any other polynomial function. Anything that would have a break in it would not be a polynomial function. It would not be continuous. All right, now we're going to talk about end behavior. The end behavior of the graph of a function to the far left or the far right is called its end behavior. So essentially, it's like what's happening at the ends of the graphs. Every graph is going to fall into one of four categories, and it's determined by two things. The leading coefficient, basically whether it's positive or negative, then the degree of the leading coefficient, or the degree of the entire function, whether it's odd or even. So these are the four categories they can fall into. What happens in the middle is undetermined by this, but what we're talking about is just how the function ends. So if a function is odd, it's going to look one of two ways. But if the function is, when we say an odd function, we're talking about degree 3, degree 5, degree 7, right? Like odd numbers. Sorry. If a degree is odd, it's going to fall and rise separately. Like one side's going to fall, one side's going to rise. The leading coefficient is going to tell you which side. So if the leading coefficient is positive, it'll fall left and rise right. If the leading coefficient is negative, it'll rise left and fall right. For even functions, so degree 2 quadratic, or degree 4, degree 6, and so on, all the even numbers, they will either both rise and fall, or they will both rise on the left and right, or they will both fall on the left and right. And it's based on, again, the leading coefficient. If the leading coefficient is positive, they both rise. If the leading coefficient is negative, they both fall. And again, every function is going to fall into one of these four categories. Again, what happens in between is determined by other factors, but how each function ends is going to be one of these four scenarios. So let's talk about what this means for an example. So here's a function, f of x equals x to the fourth minus 4x squared. Again, there's only two things I'm looking at. The degree of the function, which in this case is even, and the leading coefficient, which there is none, so it's 1, so it's positive. Um, so if that's the case, I'm going to flip back to our chart. N is even, and the leading coefficient is positive. So the function we just looked at in that example falls into this category. Both sides rise. Okay. Well, there would be that graph. Again, both sides are rising. Why don't you try both of these? I would suggest pausing the video, give yourself a chance to figure them out, and then we'll come back and we'll try them together. So for this one, for part A, the degree is odd, so it's going to be split. The fact that the leading coefficient is negative means it rises on the left and falls on the right. For part B, since the degree is odd again, they are going to be split, but since the leading coefficient is positive, it's going to be the opposite of what the last one was. So it's going to fall to the left and rise to the right. Okay. And again, that comes straight from that chart we looked at 2 slides ago. All right, use the graph of f of x equals x cubed plus 13x squared plus 10x minus 4 to determine end behavior. So in this case, we'll just graph it and take a look at what it looks like. So in order to graph, just type it in. So x cubed plus 13x squared plus 10x minus 4. Let me graph. It was suggesting doing a zoom standard. The way that you do that is hit zoom and then hit 6. That's what will probably be on your screen unless you've done something else. So what you should notice is the end behavior here. You actually can't see everything that you would expect to see, because if it's x cubed, right, you would expect to see it falling on the left and rising on the right. So what I'm going to do is a zoom fit and see if we can see the whole thing. Sort of. But it's rising on the right, and then this is going to curve back down and fall to the left. So that does kind of fit what we were talking about. This was not as clear as I was expecting it to be. All right. Zeros of a polynomial. Zeros are interchangeable with roots, solutions, and x-intercepts. They're all the same thing. So you can get them a couple different ways. I know if you think back to the objectives, it did talk about factoring. So we're going to factor to get some of them, but same thing as looking on a graph and seeing where it crosses the x-axis. So we're going to find all the zeros of these two functions. We're going to do part B. So if you take part B and you factor, we're going to factor by grouping. All right. So you take an x squared out. I'm sorry, you split it in half. You take out a GCF of x squared from the first two terms, and you get x squared times x plus 2. Out of the second two terms, you take out a -4, and it's -4 times x plus 2. Then you can factor the x plus 2 out, you're left with x squared minus 4. You set each of those separately equal to 0. And you get x plus 2 is equal to 0, so then the solution is negative 2. You get x squared minus 4 equal to 0. And you get x is equal to positive or negative 2. So you get 3 solutions, which is what we would have expected from a cubic function. But notice how negative 2 shows up twice. So there really are 2 zeros, even though, again, you had 3 solutions. Negative 2 had a multiplicity of 2 because it counted twice. So really there's just 2 solutions, negative 2 and 2. And they would be x-intercepts. This is what the graph looks like. Notice how for the 0 that had a multiplicity of 2, it touches it and turns around. For the other 0 that only has a multiplicity of 1, or no multiplicity, I suppose, it crosses through. So if r is a 0 of even multiplicity, then the graph touches the x-axis and turns around at r. That's what we saw at negative 2 in the previous example. If r is a 0 of odd multiplicity, then the graph crosses the x-axis at r. That's what we saw at positive 2 in the previous example. Regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. So what that's saying is the way that it crossed through on the last one, that was because there was no multiplicity, or the multiplicity was 1. If the multiplicity was 3, it would have still flattened out, but then it would have just turned back up. So find all the zeros of this function and then state whether the graph crosses the x-axis or touches the x-axis and turns around. So this is kind of a mess, but if you can picture this, here's the function. We set the whole function equal to 0, and then you just break it apart. So just take the x plus 1/2 squared, set that equal to 0, which essentially means x plus 1/2 equals 0. So you subtract 1/2 and you get x equals negative 1/2. So x equals negative 1/2 is one of the zeros. For x, the other factor here, x minus 5 cubed, set x minus 5 equal to 0, so you get x equals 5. So x equals 5 is one of the zeros. The negative 1/2 has a multiplicity of 2 because the exponent on that factor was 2. X equals 5 has a 0 of multiplicity 3 because the exponent on that factor was 3. Because the negative 1/2 had a multiplicity of 2, which is even, when you look at the graph here, it's hit that point and then turned around. For x equals 5, it had a multiplicity of 3. So when that 0 occurred, the function continued through, it passed through. So again, this is what it's going to look like when the exponent is even. It's going to hit and turn around. This is what it's going to look like when that exponent is odd. It's going to cross through. And seeing how that it did flatten out a bit, that's what it was talking about 2 slides ago. It flattened out a bit, but it still passed through. So this is just saying what we just talked about. The graph will touch here and then turn around. And here it's crossing through. Touching is because that number was even. Crossing through is because that number was odd. At this point, here's another example. Why don't you try it? Pause, give it a try, and then come back and then check your answer with me. So there's 1, 0 at negative 1. Positive 1. It's at negative 1. and it will cross through because the multiplicity there is 1. There's another 0 at 3/2, and it will touch and turn around because the multiplicity is 2, which is even. The intermediate value theorem. This is going to sound way more complicated than it really is. It says let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c equals 0. Equivalently, the equation f of x equals 0 has at least one real root between a and b. So basically what that's saying is, if you pick two different x values, and when you evaluate the function, one of those x values causes the function, the output to be positive, and one of those x values causes the output to be negative. That means somewhere in between, it had to cross from positive to negative through 0. So you're just able to guarantee that a 0 happens between 2 points if, when you evaluate, one side is positive, one side is negative. So here's an example where you're given a function and you're asked, does it have a real 0 between -3 and -2? Those are x values. So what you're going to do is you're going to evaluate at f, you're going to evaluate the function at -3 and at -2. And then if the signs are opposite, then the answer is yes. If they're not, then you can't guarantee that there's not a 0 in between, but you can't guarantee that there is either. But if they're opposite, you can guarantee that there is a 0 between. So when you evaluate first for -3, you end up with -42. When you evaluate for -2, you end up with 5. So they're opposite signs. So that means you can guarantee that there is a 0 between -3 and -2. That's what it's saying here. The sign change shows that the polynomial has a 0 between -3 and -2. And then when you actually graph the function, there is that 0 that is crossing between that. So here's an example that I want you to try on your own. Pause, and then come back and I can go over the answer with you. So f of 2 evaluated for -1 and f of 3 evaluated to 16. So they are opposite signs, so there is a 0 between 2 and 3. Turning points. So this is saying if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. So think about a quadratic function, right? A quick sketch here. Quadratic function looks like that, right? Its n value is 2, like the biggest exponent in a quadratic function is 2. It has 1 turning point. Think of a cubic function. That's just generically what it looks like, right? It has 2 turning points. And that is a pattern that will hold forever. So a 4th degree, I'll do one more sketch, will look like that. Okay, it has 3 turning points. A 5th degree will have 4 turning points. A 6th degree will have 5 turning points, and that will be forever. And that's also consequently, if we go back to the beginning of the lesson, when we're talking about the n behavior, well, when you keep adding 1 turning point, that's why it will the even ones will end up pointing in the same direction, and the odd ones will point in opposite directions, right? So again, out of the ones I just drew, the ones that have n values that are even have end behavior that are pointing in the same direction, whereas the one that's odd has the end behavior in opposite directions. It's all connected. All right, so at the beginning we were talking about how every bullet point there leads you to one place. So all of that stuff that we just talked about was to be able to graph polynomial functions. So the first thing you're going to do is use the leading coefficient test to determine end behavior. So at least get a general sense of what's happening. Um, what's happening on the left side and on the right side, whether it's rising or falling in both cases. So you can figure out which of those four categories your graph will fall into just by looking at the leading coefficient and the degree. The second thing is you're going to find the x-intercepts. So that's just solve whatever it is that you have, right? So we'll do that by hand in the example, but you could also use your calculator and see where the x-intercepts are that way as well. And then remember the multiplicity and the behavior, meaning when you do solve, if the multiplicity is even, it's going to touch and turn around. If the multiplicity is odd, it's going to pass through. We're going to find the y-intercept. We didn't practice that, but that's because it's as simple as you substitute 0 in for x and solve for y. So we'll do that when we do our next example. And then you're going to state the maximum number of turning points. And that's just whatever, we just talked about it, but that's just whatever n is, the turning points are going to be one less than that. All right, so we're going to graph these four. Actually, we're going to graph the first three together, and I'm going to leave the last one as an exit ticket that we'll go over in class together. Okay, so let's take a look. So we're going to go through that whole strategy list. First thing is the end behavior. Even degree and positive leading coefficient. So that means it's going to rise left and it's going to rise right. And again, refer back to that chart earlier in the notes for if you need to look at that. So I already know that it's going to rise to the left and it's going to rise to the right. What happens in between, we're going to also figure out. But let's figure out the x-intercepts now. So let's try to factor this. This is a quartic function that's in quadratic form. So I'm going to try to just factor it like it's a trinomial, like a quadratic trinomial. So if it's x to the fourth, I'm going to have x squared there and x squared there. What multiplies to positive 1 and adds a negative 2 will be minus 1 and minus 1. So what you're going to end up with is x plus 1 times x minus 1 times x plus 1 times x minus 1. So you get 4 solutions, but it's really just 2 because you get x equals negative 1 there, x equals 1 there, x equals negative 1 there, and x equals positive 1 there. So you end up with x equals negative 1 with a multiplicity of 2, and x equals positive 1 with a multiplicity of 2. We're also going to find the y-intercept. So again, y-intercept is just what is f of 0, meaning substitute 0 in for there and there. So that's gone, and the only thing left is 1. Basically, the y-intercept is going to be the constant in whatever the function is. So we can also plot that. And then how many turning points? Well, n is 4, so there are 3 turning points. So that's enough information to get a pretty reasonable sketch of what this graph is going to look like. So let's start with just plotting the intercepts. The x-intercept at negative 1. There's an x-intercept at positive 1. And there's a y-intercept at positive 1. Okay. There are 3 turning points. Also, given that these are even, they are touch and turn around, not pass through. So the fact that I know it rises to the left means it's moving from left to right. It's coming down this direction. It's going to, I want to make it clear that I am touching and turning around and not passing through. So we pass through, we touch here, we come back down, we touch and turn around, and then it ends up heading back up. Again, our end behavior is rising on the left and the right. My x-intercepts are touch and turn around. It does go through that y-intercept. It has 3 turns. While not a great drawing, it has the characteristics of what this graph actually will be. Okay. I suggest for the next two, pause and I'll talk you through it. And then again, on the last one, you're going to do it, and then we'll talk through it in class. So we know that it's going to fall to the left and rise to the right based on the degree and the coefficient. The x-intercepts, once I factored, I did GCF, then just set them equal to 0. And when x squared equals 0, you get x equals 0, but that has a multiplicity of 2. X equals 3 is no multiplicity, so it's considered odd. The y-intercept is substituting 0 in for both, you get 0. So the y-intercept is going to be 0, and this will turn twice. So let's put all that together on the graph. You have x-intercepts at 0 and 3. The y-intercept 0, so we already have that. So that doesn't give us another point, but at least we see it. It does fall to the left. That means it's going to be coming up from the bottom here. 0 is an even multiplicity, so that touches and turns around. And then at some point here, it turns again, and it will pass through our 0 at 3, and it will continue then to rise to the right forever. So that is what your graph will look like there. Right, again, I would pause here. I'll go through it. You can unpause and then check your answer. The trickiest part about this is right what I have written up here. This is actually degree 3. I get that the biggest exponent is 2, but this is all one term. So there's 2 x's here and there's another x here, so it's a total of 3. It's not like these are 2 separate terms. Okay, this is one term, so this is degree 3. It's just already factored. So that means it's based on the leading coefficient being negative. It rises to the left and it falls to the right. That's the category it will fall into. In terms of the x-intercepts, you just take the 2 factors, set them equal to 0. For x minus 1, you're going to get x equals 1. For x plus 2, you're going to get x equals negative 2. The y-intercept is where you substitute 0 in for x and solve, and you get negative 4. And there will be 2 turns based on this being degree 3. So again, that's probably the toughest part. So if you only had degree 2 there, then that would have messed it up. Let's plot the points, the x-intercepts and the y-intercept. So you have one x-intercept at 1. You have another at negative 2. And then you have a y-intercept at negative 4 down here. Okay. It rises to the left. So that means we're going to come down from this direction to get to that x-intercept. Again, the x-intercept at negative 2 is it has a multiplicity of 1, so this will pass right through. It's got a y-intercept of negative 4, so we'll touch that. It will turn there, come back up to the x-intercept of 1. That has a multiplicity of 2, meaning it turns. We've gotten both of our 2 turns now, and it does fall to the right, so we're done. All right, so your graph is going to look like that, roughly. But at least those characteristics of the intercepts and the touching and turning there and the passing through there. Okay. Like I said, the last one I'm going to leave for you to try on your own. And I do have a Google form where I want you to just submit what your answer is. And then we'll talk about it in class. We'll go over it together. Okay. Let me know if you have any other questions. We'll go over this in class first thing on Thursday, by the way. All right. Let me know if you have any other questions.